Hi class, thanks for tuning in. This lecture is going to set us up for the exercise in Strawberry Creek, and the topic of the lecture will be measuring and modeling discharge. There's also a second mini lecture that I'd like for you to watch before Thursday because it's going to talk about one more technique that we will use to measure discharge that I won't talk about in this particular lecture. So today I'm going to go over some characteristics of flow in rivers, which you'll be able to see with your own eyes on Tuesday. Then we'll talk about some common equations that are used to model discharge, and then we'll talk about direct measurements of discharge using engineering structures called weirs and using the method that we'll embark upon on Tuesday. Then we'll talk about some tricks of the trade for acquiring velocity measurements, and we'll talk about rating curves, which relate the level of water in the river to discharge. So just as a reminder, one of the things we talked about in class on Thursday was an important non-dimensional number in hydrology called the Froude number. The Froude number was a ratio of inertial to gravitational forces. And it let us know whether the flow was supercritical, which has very high velocities but low water depths, or subcritical, which tends to have lower velocities but higher water depths. Now, an even more important non-dimensional number than the Froude number that's commonly used in hydrology is called the Reynolds number. The Reynolds number is a ratio of inertial to viscous forces in flow. So you could think of inertial forces as the forces that are related to the speed of water, whereas the viscous forces are the forces within the water that actually resist flow. Viscosity is a property of water. That is a rough measure. You can think of it as a rough measure of how sticky the water is. Paint, for instance, has a very high viscosity, whereas water has a low viscosity relative to paint. Now, the Reynolds number is important because it tells us whether a flow is turbulent, laminar, or transitional. And the main way that you could tell turbulent flow apart from laminar or transitional flow is by looking at individual streamlines within the flow. And individual streamlines in turbulent flow tend to trace out eddies. These eddies have a variety of different length scales and different time scales. Some of them spin faster than others, some of them spin slower than others. But in general, these streamlines are fairly chaotic. So this is turbulent flow. Laminar flow, in contrast, tends to have very smooth, parallel streamlines, very orderly. And transitional flow is transitional between those two end members. The flow streamlines might look a little bit like this. You might get an eddy forming occasionally. Other times you might have relatively straight or smooth streamlines. So this is laminar, and then this case that I just drew is transitional. Now, there are threshold Reynolds numbers that separate these three different flow cases, where low Reynolds numbers refer to laminar flow, high Reynolds numbers refer to turbulent flow, and then intermediate Reynolds numbers refer to transitional flow. Here's just another depiction of what those streamlines look like. This is looking down on a stream, and one of the things that you'll notice is that if we look close to the wall for this laminar flow case, you'll see that the magnitude of the velocity, which is represented by the length of the arrow, gets very small. Well, in fact, it actually does go to 0 at the wall. So velocity at the wall equals 0. And this is as a result of friction. Now, we call this the no-slip condition in hydrology. Now, the no-slip condition doesn't just apply to laminar flow. It also applies to turbulent flow. It applies in all cases, in fact. The reason why this top diagram doesn't show streamlines going to 0 near the walls is that this is a phenomenon that happens very close to the wall within turbulent flow. And in fact, if you were to look at a vertical velocity profile in turbulent flow, so this is the vertical coordinate on the y-axis and the magnitude of velocity on the x-axis, what you see is that very close to the wall there's a very steep increase in velocity, and then that velocity becomes relatively consistent as you move further up within the flow. Now, it turns out that in turbulent flows, these vertical velocity profiles are logarithmic, Whereas with laminar flow, if we were to draw the same vertical velocity profiles, we would find that they're parabolic. And so with laminar flow, velocity continues to increase fairly steadily as you move away from the wall. So this is parabolic. Now, most natural streams do have turbulent flow. One exception is the Everglades, where I work, which has laminar to transitional flow. But many equations for calculating discharge, many experimental methods for measuring discharge rely on the assumption that the flow is turbulent. Now, if the flow is turbulent and has one of these logarithmic velocity profiles like I've depicted here, then it turns out that the depth average velocity happens at 0.6 of the way down the water column. So let me clarify. So let's say this is the water surface up here at a point that is 60% of the water depth. The velocity measured at that location is equal to the depth average velocity. This is something that's very important in the measurements we'll be making in Strawberry Creek. So just to make this diagram complete, it's 0.6 of the way down the water column, which means it's 0.4 of the way up. Okay? So this is just another depiction of a transition from laminar flow, where the streamlines are roughly parallel but very smooth, to transitional flow, where they start to develop some undulations, to fully turbulent flow, where you get these eddies fully developed close to the bed because of the no-slip condition. We go back to transitional to laminar flow, and velocities near the bed are much slower, tapering down to zero. But within the turbulent region, velocities are relatively consistent with depth. So this also applies if we look down on a stream, because there's also a no-slip condition at the stream banks. You'll also see velocity going down to about zero at the stream banks, so no slip applies here. Whereas in the center of the channel, in these regions, velocity ends up being the fastest. If we look vertically in a stream, again, because of this no slip condition, we see velocity profiles going down to zero near the bed, and they become much more consistent as you move further up within the water column, particularly if we're talking about turbulent flow, which almost all rivers are. So it turns out, though, that it's not always the case that the fastest flow occurs in the dead center of the river, and this is because rivers tend to have highly variable cross-sectional geometry, which depends on whether you're talking about flow across a meander bend in a river or flow across a straight section of a river. So if you walk downstream in the Merced River at this location near Yosemite, what you'll see is that you have these skewed cross-sectional profiles, and then it gets skewed in the other direction. This one is fairly rectangular in shape, and then this one's a little bit different still. So what's going on here? Oh, let me go ahead. I'll come back to that. So what's going on here is that when flow goes around a meander bend, you could think of it as tracing out the trajectories of that, say, an ant would trace out sitting on the outside of a spinning disc or a spinning record. So in these meander bends, the flow curves, and streamlines that are at the outer edge of the curve end up moving much faster than streamlines on the inner part of the curve. So this is high velocity, and this is low velocity. And this has consequences for sediment transport. It turns out where there are regions of high velocity, there's a lot more scour, and so you could develop very deep portions of the river close to the outer part of the river bend, as is being depicted right here. Whereas the inner part of the river bend gets a lot of sediment deposition because slower flow is just simply less able to carry sediment. And so you have much shallower cross sections near the inner part of river bends. Now, in straight sections, you do tend to develop much more even, symmetrical, almost rectangular profile. So if we look at rivers, at several different cross sections of a river that's going around a series of meander bends, what you see is that at A, the highest velocity part of the river is near the outer part of the bend. Again, it doesn't touch the bank because the no slip condition not only applies at the bed, but it applies at the bank. And we could emphasize that here. So this no slip condition applies all along the wetted perimeter of the river. Now, the fastest flowing water does tend to cause erosion at or near the bank, and this can lead to bank undercutting and the formation of almost these cliff-like features around the bank. These are called cut banks, like what you see here, and the cut bank on this diagram is these brown areas. Whereas on the inner part of the river bend, you get deposition, and this forms sand and gravel bars that you'll see if you're canoeing or kayaking down a river. So these are called point bars. And it's only really in the space between the two meander bends where you develop these nice rectangular cross sections where the maximum velocity core is near the center of that section of the river. Another thing that is the distribution of flow velocities in rivers is their cross-sectional area. Now, remember the principle of continuity that we talked about last Thursday. So the continuity principle tells us that the discharge has to equal the velocity times the cross-sectional area. And if you don't have any inflows or outflows to a river along a section of interest, then this Q is going to be a constant. Constant where no inflows or outflows. And so if we're looking at a section of river like the one that's depicted here, you can see that the presence of this bridge narrows the cross-sectional area, and therefore you would expect much faster flow immediately under the bridge than in the upstream or the downstream location. Something that we do see in reality. So here's an example of a bridge that narrows the cross-sectional area of flow, and you can actually see this induces a transition from subcritical flow here, which has a higher water depth, to supercritical flow down here, which is faster and has a lower water depth. You could also see there are these hydraulic jumps that form in the vicinity of these bridge piers. This flow is highly turbulent, and it's likely that there's a lot of erosion happening around these bridge piers. So along, we're going to start talking about how we actually can estimate discharge using equations or directly measure discharge using experimental techniques. And to start this discussion, I want to remind us of the hose problem that we talked about a little bit earlier. I want to go over this again because I think I told you one thing wrong in class about this hose. So let's just draw the situation. We have a wall, we have a hose coming out of that wall. Hoses are usually green. So the hose rested on the ground, and then it went over a stool, and then it had an outlet further on against the ground. Okay. So it looked something like this. And what we had done earlier is we solved the Bernoulli equation to figure out the height of these leaks of water happening at point A and at point B. We were given the velocity at the outlet of the hose. So just as a reminder, going back to the solution for the height of the spigot at A, we could say that at the top of the spigot, or at the top of the sprinkler, I should say, velocity is 0. let me just go ahead and write the Bernoulli equation as a reminder, first of all. So the Bernoulli equation is u squared over 2g plus p over rho g plus z equals the total head, where the first term over here is the velocity head, this is the pressure head, and this is the elevation head. So going back and solving for z sub a, let me just do this in a different color for clarity. We'll pick pink. So at the top of the sprinkler, right here, we have a u of 0. Then we also have a pressure of 0, because remember we're dealing with gauge pressure and we're at atmospheric pressure at the top of this sprinkler. And then we do have an elevation head, which is equal to ZA. This is the thing that we're trying to solve for. Now we could say that this is equal to the total head at point A, and in turn the total head at point A is equal to the total head at the outlet. So let me just emphasize these points. So all three locations are connected by streamlines and have the same h. So as a result, we can set this value of h, which we just calculated, as equal to the h at the outlet of the hose. At the outlet of the hose, we have our measured velocity, u naught squared over 2g. Again, the pressure is atmospheric pressure, so this is 0, and the hose is resting on the ground, so the elevation head is also 0. So with this information, we're able to solve for the height of the sprinkler at A. So how about at B? Let's now choose a different color. I'll go with orange. So at B, we can say that the total head is equal to the total head down here at the point of the leak and the total head at the outlet here, because there's a streamline from this point to this point, and there's also a streamline from this point to this point. So at these orange locations too, the head is equivalent. Well, we already know what the total head is at the outlet of the hose, and so in order to solve for z sub b, we could set up a very similar type of equation where h equals, again, velocity at the top of the sprinkler is equal to 0. We're at atmospheric pressure, which is a 0 gauge pressure, plus the height of the sprinkler, but the base of the sprinkler is some height above the ground. It's equal to the height of the stool, which I'll just call ZS. So I have to add that. And we could, again, set this equal to the total head at the outlet, which is u naught squared over 2g. So what we see, therefore, is that ZB equals u naught squared over 2g minus z sub s. You'll note, though, that u naught squared over 2g is just equal to z sub a according to this equation. So what we could say then is that z sub b equals z sub a minus z sub s. So in other words, z sub s plus z sub b equals z sub a. So what we see actually is that in this particular case, the two sprinklers rise to exactly the same height. Okay? So what happens in reality? Well, if you were to do this in reality, let's just say we have a hose like this. I'm just going to draw it with a slightly different configuration. Now we just have a hose that's coming out of the wall and falling to the ground. And again, we have 2 points along this hose that we're interested in, points A and points B. So if we were to do this in reality, what we would actually observe is something a little bit different than what I just showed with those equations. So, if we do this in reality, what we see is that the sprinkler at A might rise to that level, whereas the sprinkler at B rises to something lower rather than to the same level. So maybe this isn't too surprising, because one of the things that one of the things we didn't include in the Bernoulli equation already is friction. So friction is what's going on here. So let's just go ahead and define some terms. Let me draw a straight line here. So there appears to be a loss in total head between points A and point B here. And this is something that actually is defined as a true loss. So if you were to just draw a horizontal between A and B, the distance between the horizontal and the level at which the sprinkler at B actually rises is what is referred to as the head loss, or H sub L. And I'll just define another thing, which is the distance between A and B, which I'll call L. So we could actually rewrite the Bernoulli equation in a way that accounts for friction. And the way that we would do this is to write U sub A squared over 2G plus the pressure at A over rho G plus the elevation at A equals U sub B squared over 2G plus the pressure at B over rho times G plus ZB plus this head loss term. And when we account for head loss in this way, just by adding it to the elevation head, we can say that this truly is equal to total head, which is a constant. So this is a form of the Bernoulli equation that accounts for friction. Okay. So before I go on, I'm just going to stop here so that no one of these videos becomes too long to download and to upload. So I will continue this in a part 2 of this particular lecture.